Hello there, Mr. Sutton bringing you the AB Calculus Chapter 4, Quiz 4 review solutions on motion, optimization, and related rates. For this problem, we have a clown jumping on a trampoline with a height given by this formula here. Based off of that, we want the average velocity of the clown during the first 3 seconds. So we're essentially just using the AROC formula on this expression, which has a name of S. So we're going to do S of 3 minus S of 0, because they said first 3 seconds, all over 3 minus 0. So now we're going to plug S, or 3 and 0, into the S function. So let's see, we've got 50 times 3, that's 150. This is 5 times 9, which is 45. So we have 150 minus 45, which is 105. And then if you do S of 0, that just zeroes everything out. So you've essentially just got 105 over 3, which comes out to 35. And what are the units going to be on this? Well, since it's velocity, that's going to be, in this case, feet per second. For this problem, we want the clown's velocity at 6 seconds. So for that, we need the instantaneous rate of change, S prime, or V. So I'm going to start by writing V of t equals S prime, just to show people where I'm getting my velocity function from. And then S prime is just going to be 50 minus 10t. So now I just have to plug 6 into my S prime here. So that's 50 minus 10 times 6. 50 minus 60 gives us negative 10, and that is going to be in feet per second. For this problem, we want to know the maximum height the clown reaches. So just maximizing functions in general, we want to know where the derivative of the function we're trying to maximize equals 0. So I'm going to let S prime, which again is 50 minus 10t, equal 0. And where does that equal 0? Well, if you subtract 50 and divide by negative 10, then that reaches 0 at time 5. So, I mean, we can think about this intuitively since a clown is jumping up in the air, and this is the only critical value, and then the clown presumably falls back to the earth or the trampoline. This has got to be the time that the clown reaches the maximum value. But to really rigorously prove that, we would need the first or the second derivative tests. First derivative test, you could do sign analysis around 5. So a little bit to the left of 5, like if you plug in 3, you'll see that this is coming out to a positive number. And if you plug in something bigger than 5, this comes out negative. Since S prime changes positive to negative at t equals 5, we could say there's a max there. Another way to do it would be with the second derivative. So S double prime is just going to be negative 10. And since the second derivative at 5 is negative, I mean it's negative everywhere because it's a constant, that tells us by the second derivative test that this is going to be a max. So we actually have to find the max value by plugging 5 back into the S function here. So that's going to be 5, or 50 times 5, which is 250. We're subtracting, let's see, 5 times 25 is 150. So 250 minus 125 then is going to be 125. There we go. For this problem part, we want the acceleration of the clown when the velocity is 0. So we can't just plug 0 into the acceleration formula that we're going to come up with because 0 is not a time. Acceleration takes an input of time and gives you an output of acceleration, the rate of change of velocity. So we need to figure out what time this velocity actually happens at. Now we saw on the last problem part, if we set S prime equal to 0 and solve, that t equals 5 when our velocity, or S prime, equals 0. So 5 is what we're going to have to plug into the acceleration formula. Acceleration is the second derivative of position, or the first derivative of velocity. Since we already had a velocity formula from before of 50 minus 10t, acceleration is just one more derivative on that, so that would just be negative 10. This is the S double prime that we actually used in part C. So the acceleration then is always going to be negative 10. I mean, if there was a place to plug in for t, we would. But, I mean, if you do a of 5 or a of anything on here, you're going to get negative 10. So this acceleration is going to be constant regardless of time, meaning we end up with negative 10, and the units on that is going to be feet per second squared. For this problem, we have a bat flying back and forth along a straight line with a position given by this crazy formula, and this gives us feet as output, and the input is going to be seconds. So we want to know when, for t greater than 0, does the bat change directions. If I'm talking about a direction change, I'm talking about places where s prime, the derivative of this, the rate of change of this, is changing sign. So I need to figure out s prime first. That's going to be, and that's also the same as my velocity. So that's going to be 8t cubed minus 72t, and that 40 is gone because the derivative of that is 0. So we need to know when this function changes direction or changes sign. So we need to figure out where it equals 0 to start off. So solving for t when this equals 0, we can factor out an 8t, leaving us with t squared minus 9 inside. And then if you wanted to, you could factor this a little further. This is t plus 3 and t minus 3. So then we see t is going to equal 0, negative 3, and positive 3. So this is places we might need to do some sign analysis around. But if you look back at the problem, it says t greater than 0. So we actually can ignore 0 and negative 3 and just consider what's happening at 3 seconds. So let's go ahead and make a number line. This is for the velocity. And here's 0 at the beginning because I don't want to test anything before 0. So I'm just going to put that in my number line as kind of an endpoint. And then I also have the 3 seconds that is my other critical value I'm considering. So a number between 0 and 3, I'm going to choose 1. That's pretty easy. If I plug 1 in my velocity, that's going to give me, let's see, positive, positive, negative. That's a negative overall, odd number of negatives. If I plug in something bigger than 3, like 4, that gives me a positive, a positive, a positive, so positive overall. So since we have a sign change for my velocity, v of t at x, or t equals 3, that means that therefore the bat is changing directions at 3 seconds. For this next question, we want to know the velocity and the acceleration of the bat whose position formula is given up here. We want those at 2 seconds, and then we want to know if the bat is speeding up or slowing down at that time. So let's start with velocity. That's going to be 8t cubed minus 72t. That's the formula for velocity. So plugging 2 into all that, 8 times 2 cubed minus 72 times 2. You could use a calculator on this. That ends up being, let's see, 64 minus 144, so negative 80. The units on that is going to be feet per second. Next, let's find the acceleration. Acceleration is the derivative of velocity. So that's going to be, let's see, 24t squared minus 72 in general. And then if I plug 2 into that, that's 24 times 2 squared minus 72. So 4 times 24, that's 96. Subtract 72, and that's going to come out to 24. That's going to be feet per second squared. And now the question is, our bat speeding up or slowing down? So for this, you have to consider both the velocity and the acceleration. In general, if the velocity and the acceleration have the same sign so that they are working together, we would say the object or creature or whatever is speeding up. If, like in this situation, the velocity and the acceleration have opposite signs, then they're working against each other. This bat is flying, I guess, backwards or whatever, but there's other forces pulling it the other way, so that this negative is becoming less and less negative as we go. So we would say since the v and a of t have opposite signs, therefore the bat is slowing down at time 2 seconds. For this problem, we have a spherical balloon inflated with gas at the rate given here. We want to know how fast is the radius of the balloon increasing at the instant the radius is 2 feet. So if we're talking about instant values and multiple rates of change, we're talking about related rates, which means I need to write a formula that ties all of these things together and implicitly differentiate it with respect to time. So my formula, we're talking about the volume of a sphere. So that's going to be volume V equals 4/3 pi r cubed. And now I'm going to take the derivative of both sides with respect to time. So V, that derivative is going to be dv over dt. On the right side, these 3's are going to cancel when I multiply, so that's just 4 pi r squared dr over dt. Any letter you take the derivative of, you have to put a tail next to it with d that letter over dt. All right, so let's take stock of what we have and what we don't. So they told me my gas was going in there at a rate of 20 feet cubed per minute. So that means 20 is my dV over dt, my rate of change of volume. They also told me that the radius is 2 feet at some point, so r is 2. And they want to know how fast the radius is increasing, so we're actually solving for dr over dt. There's no other unknowns in here, so let me plug in the things that I have and solve for the thing that I don't. So I can then write 20 equals 4 pi 2 squared dr dt. This is really, let's see, 4 times 2 squared, that's 16 pi, and I can divide both sides by that. So if I stick units next to this on a free response, this is the final answer, but I might need to get a decimal for multiple choice or something. And at this point, we're going to need to use the calculator to get our final decimal answer. So go into Desmos, let's do 20 divided by 16 pi for pi, and that's about 0.398, and those units are going to be in feet per minute. For this problem, I have a 17-foot ladder leaning against a wall, so I'm just going to draw a little diagram here. This is going to give us a right triangle, and it's a 17-foot ladder, so this is the ladder leaning, so that's actually the hypotenuse of this right triangle. So now we have the bottom of the ladders pulled along the ground away from a wall at a constant rate of 5 feet per second. How fast will the top of the ladder, up here, be moving down the wall when the ladder is 8 feet above the ground? So we have multiple rates of change going on. We have the horizontal rate of change and a vertical rate of change. We have some instant values. This 8 is an instant value, as opposed to the 17, which the ladder's always 17 feet. It's not always 8 feet above the ground. So this is a related rates problem. I'm going to get some more variables, write an equation that ties all of this together, and then see if I can solve for the rate of change that I'm looking for. So I'm going to label this. I'm going to call this horizontal piece x, and I'm going to call this y, because x is left, right, and y is up, down. It just makes more sense that way. And what ties all these together, since this is a right triangle and these are sides, we can talk about this with the Pythagorean theorem. We can say that x squared plus y squared equals 17 squared. And at this point, now that I've got something that ties everything together, I'm going to take the derivative implicitly with respect to time. So the derivative of x squared, that's going to be 2x dx over dt. This will be 2y dy over dt. And the derivative of this constant is just 0. All right. Let me take stock of what I have now, and we'll see what else we still need to find. So just reading through here again, the bottom of the ladder is pulled along the ground away from the wall at a constant rate of 5 feet per second. So that's the rate of change of this x down here. So if this is being pulled away, it's getting bigger, which means that this is a positive 5 feet per second. You always have to be conscious of whether it's negative or positive, but that's growing at a rate of 5. Next, let's see, how fast will the top of the ladder be moving down the wall? So that's talking about dy over dt. And when it is 8 feet above the ground, we're saying that this y value at some point in time takes on a value of 8. So y equals 8 at some point in time. So I've got y. I'm looking for dy over dt. I've got dx over dt. I still need to find x, though, at the time when y equals 8. Once I have that, I can plug in everything and solve for dy over dt. Well, the good news is the Pythagorean theorem still works. If I want to find x, I just need to take the square root of c squared minus a squared, or 17 squared minus, in this case, 8 squared. So if I do that, let's see here, I'll use my calculator for this. Actually, I really shouldn't need to. I mean, this is an 8, 15, 17 triangle. But if you do use your calculator, it comes out to 15, if you didn't recognize one of those special Pythagorean triplets. So now that I've got all my missing pieces, except for the thing that I'm solving for, let me plug it all in. We're going to have 2 times the 15 that we just found, times 5, plus 2 times the y value 8 that they gave us, times dy over dt equals 0. Doing a little bit more to solve, This all comes out to 150, which I'll move over here. 2 times 8 is 16. Dividing both sides by 16, let me see what the calculator gives me for that. And then let's just divide both sides by 16 to get our final answer. So we've got negative 150 divided by 16 coming out to negative 9.375, and that is going to be in units of feet per second.